Hello, everyone. Welcome to my new lecture, or part of my lecture. It's about the paging and segmentation. So this is so this part is within the context of the memory management, which I usually explain during my operating system course. So I will start first by sharing my screen, and then I will go into describing the paging steps and also how the physical address is generated from the virtual address or logical address. And then we'll move into the segmentation, and I will show also the difference between segmentation and paging, especially when it comes to the memory partitioning, and also how the physical address is generated. So I will start by sharing my screen. Okay. So this is the how the virtual memory and paging. This is the just to give you an overview. So here you have a different process, and here the process it has either a segmentation table or a page table, and this will generate. So usually the CPU will generate the virtual address, and from the virtual address it will be generated physical address, and the physical address will be used to access to the memory location, either to retrieve data or to retrieve the instruction. Okay, so sometimes if the address does not exist, then it will generate what we call a page fault. So the paging is a technique for managing the memory, in which the memory, which is split into equal size, fixed and equal size chunks, usually very small. And also the same goes with the process. So the process will be split into fixed equal size chunks, but small. And then the placement will be in this following way. So I'll take this example. So here it's the example is shown into five different steps, six different steps. So here initially the memory is empty. So there are 15 available frames. So the frames are from 0 till 14. And then suppose that I have a new process, the process A. So the process A has 4 pages, page 0, 1, 2, and 3. So since the memory is empty, so the process will be so the pages will occupy the upper part of the memory. So that will be placed in A0, A1, A2, and A3. Now, suppose that after a while there is a process B which needs to be placed, which be loaded. So the process B has 3 pages, B0, B1, and B2. So the operating system will place it next to the last one. So the last one was A3. So the next will be filled by B0, B1, and B2. So in total, I have 7 pages, 7 frames which are occupied, and the remaining are free. So the seven next are free. Now, suppose I have a new process, which is a process C. It has 5 pages, 4 pages from 0 to 3. Those also will be placed in the next free frames from 7 till 10. suppose that a process B needs to be swapped out, either because it is done or because it is blocked, and we need to free the memory. So here, the B will be swapped, and we'll have available non-contiguous parts of the memory, which is frames 4, 5, 6, and then 11, 12, 13, 14. Suppose that I have a process D that needs to be loaded. So the process D has 5 pages from 0 till 4, D0 till 4. So the D0, D1, D2 will be placed from 4 to 5, 6, and then the remaining 3 and 4 will be placed at frame 11 and 12. So this is at the step number F. So if you look at the page table, because the page table, it's a part of the process and has to be updated by the operating system, so that the operating system knows how to access the different pages of the same process. So for example, if I look at process A, so the process A the page table will be 0, 1, 2, and 3, because if you look at the last step in F, A0 has not been swapped out, so it's still in frame number 0, 1, 2, and 3. So that's why it is, so the page 0 is in 0, the page 1 is in frame 1, the page 2 is in frame 2, and the page 3 is on frame 3. Now, since the process B is swapped out, so the page is empty here. Now, for the process C, so the page 0 will be placed in 7. Okay, so process C is page 0 will be placed in 7. Page 1 will be placed in 8, page 2 will be placed in 9, page 3 will be placed in 10. The same goes with the process D, and the free frames are 13 and 14. So how the address are generated. So I will take the simplest case, which is the page size R of power of 2. This is very convenient way because it makes the memory management simple, and also the memory will be transparent to the user. So here, suppose that the CPU generated an address 1502. This is in decimal. So this will be converted into a binary. And suppose that my logical address will be of length 16 bits. So the first 10 bits will be used as a offset. So here, so the first step you have to convert into binary, and then from the binary you have to have two parts. Well, page number will offset. So the offset will occupy the 10 first bits, and the remaining one will be the page. So the page will be coded onto 6 bits. So in total, I will have 2 to the power 6 pages, and each page will have 1 kilobyte, because I have 10 bits. So 2 to the power 10, which is equal to 1 kilobyte. So how to know the physical address? So here it means that so the physical address will be located in page 1, and within the page 1 we have to move 478 in decimal. So this will be the representation of this binary into decimal. I will come later to this segmentation. So how the address are translated from logical into physical. So here we'll be using the 16 bits. So the first 6 bits from the MSB are designated to contain the page address, the page number, and the remaining are the offset. So the first 6 bits from the MSB will be used to locate the address which is located in the process page table. Remember that each process has a table. So here it means that process, so the page 1, so here it will be located into this address. So here the physical address will be done by this way. So it will copy this one as the frame, and the offset will be in this way. So this is how the physical address are generated from the logical address. Now the segmentation, because the paging is based on the fixed size, but remember that if you have, for example, a process that consumes 80 kilobyte, so you have to round to the nearest one. So 80, which means that we have to move to 128, because the next one will be to the power 8. So that's why it generates what we call internal fragmentation. So to circumvent this, so the scientists come up with a new way of doing memory partitioning, which is based on segmentation. So segmentation is It's a way to divide the memory into variable length, and there is also a maximum length for each segment. So in each segment, we'll have two parts similar to the paging. So we have a segment number and an offset. So segmentation is typically similar to the dynamic partitioning, which will eliminate the internal fragmentation. So how it works? So this is the segmentation. So I will take the same example here. So here I have the physical address, which is 1502. This will be translated into the binary representation. And since I have a variable address, a variable size of the segments, so the first 4 bits, as an example, will be considered as the segment number. So I have here, for example, two segments, segment number 0 and segment number 1. So 001, it means that so the physical address will be located into the first segment, and the remaining part will be located as the address of or the offset of the segmentation. Remember, sometimes the offset will exceed the length of the segment. So if this occurs, then there will be an error, and that I'll explain it with the graph what it means is, and then the system will crash. So that will be an invalid address. So the segmentation, so it is usually visible to the programmer. It's also a very convenient way to organize programs and data. So if a programmer writes his own code, so the code will have two parts: the instruction and also the data. So each one will be replaced in different segments. For example, in 8086, the code segment will contain the instructions. The data segment will be pointed by DTS data segment register. So how the address are translated. So number one, so the first step, the CPU or the operating system will extract the segment number. So suppose that they have n plus m. So n will be considered as the segment number, which is coded in binary, and m is the offset. So in total, the address will contain n plus m. For example, in our previous example, we have 16, so 4 plus 12. So 4 bits will be allocated to describe the segment, and the remaining will be the so the remaining will be the offset. So the the segment number after the segment, there will be an offset. So the operating system will compare the offset and also with the length of the segment. So if the offset exceeds the length of the segment, then there will be an error. Else, it will generate an address. So the address will be the sum of the sum of the starting physical address and the segment address. And this is described in the following figure. So here I have the 16-bit logical address. So 4-bit segment will be describe the segment number and the remaining address. So here we look at, so here I have the segment number 1. I have this address, and this will be used to do the sum. So the sum, this plus this will give the final physical address. And this is how the CPU gets the physical address. And remember that the physical address will be computed by the memory management unit. Thank you so much for your attention, and I look forward to having you in the upcoming videos.